Hello, so I decided that there will be another part of basics of university maths course after all. That is because I'd like to have the sigma notation in particular explained um, within some general preparatory framework because there are multiple places where we have already used sigma notation, in particular the videos on the matrix arithmetics, but I wouldn't like to link every time the videos in matrix arithmetics to just have sigma notation. That's why I would like to explain it somewhere where one could theoretically uh, logically go to any other courses. So, based on what one could consider looking at any other courses where we could need it, in particular the course on Calculus 1. Okay, so and on the other hand, I also would like to give more detailed and first of all more complete explanation of the sigma notation and of what one can do with it. Basics of University Maths Part 5. I wasn't quite satisfied with how I just briefly sketched the sigma notation in the video matrix arithmetics, and so I would like to do it in a more proper fashion just in this course that is considered general preparation for other courses on university maths that I'm doing. Right. All right. So let's dig right in. Sigma notation. Let f from 1 to n be a map into the real numbers, but generally for sigma notation we could have a map that just goes into any structure where addition or multiplication works. So that is where addition or multiplication is defined. Just think of it in abstract terms, some structure in which we can comprehensively add or multiply objects, but let's consider only the most simple case that we go into real numbers. Other cases are just the same structurally, but uh, we would have to specify the algebraic structures right here to understand what it means that we can add or multiply something in a more general fashion, and I wouldn't like to do that. But if you would like to see the application of a sigma notation in more general context, where we do not just have elements of R, but elements of different structures that we add or multiply, and just go to the video series Matrix Arithmetics. There I use the sigma notation extensively to show the basic operations in matrices and to prove things about them. Right. And I would recommend anyway that you certainly should watch those videos in matrix arithmetics because at the latest for calculus 2 we'll need matrices, so that will be important, and maybe also some examples in calculus 1 might involve matrices. Don't know yet. So I would certainly recommend to watch it. And matrices generally are important tool in mathematics, important, very basic tool. And yeah, so actually videos and matrices could be included in basics of university math, but I just didn't do it because it's not necessarily customary. Okay, let f be a function from 1 to n, or let's say not 1 to n, k to n, where kn are just given nature numbers. Alright? Okay. And then we have such a function. Then we just define a symbol that allows us to sum over such um, function, in the sense that we sum up all the images of all those points, because we have just finitely many points. There is some natural numbers are actually it is not clear here that it is finitely many. So let's say just yeah, well, if we denote it like that, it is actually finitely many, but because if, yeah, of course, what am I talking about? If we have highest number here, then of course it is finitely many, because up to there we can have maximal number of numbers equal to its numbers, so of course it is automatically finitely many. So then we just define the symbol in the following way. This is a symbol that is defined for such a given function, and it is just defined as f of k plus f of k plus 1 plus plus, and so we sum up all the uh, values of f that are respectively taken at those elements. If it is equal values, then of course they appear here indeed, because we don't care, we just sum all of that up. Alright, then there is another thing, that is sigma product. And sigma product just does the following. It does same, but it does that with the operation multiplication. And as I said, if we have homogeneous structure where multiplication and addition is admissible, then of course we can do the same for that structure. Alright, let's look at some examples. And here it is important to understand that a function or a map in that context is really understood very broadly, and it is used very broadly, right? So this is just some map. So for example, what we could have, I don't know, for example, 1 to 5, right? Those are just numbers, k equal 1 and n equal 5. And by the way, usually by use of such notation, you do not necessarily specify directly the function. And that could be just some index numbers. So basically, this is of course a1 plus a2. And of course, those numbers are defined somewhere, right? And you do not specify this function, you do not write it down like I is mapped to AI. No one does that. people just write that down. It is clear that it is this function that is meant because the notation already structurally contains it. Right, now we could have some, I don't know, of course it doesn't matter what we call indices, but if there is some notation of this sort and there are some letters like this, then of course natural numbers are meant, and this is just also some natural numbers, some natural number to which we go, and we have to go through all of it, and this is here more familiar example of function, but restricted to discrete points, right? Discrete points meaning that we only take natural numbers as the arguments and we map to corresponding images, right? But as I said, does that we just write it down and we know what is meant. It meant s squared plus s plus 1 squared plus m squared. So we go through all of it and we start by s, and this is the rule of what we do with the object to get the proper sum term. So to get the sum term which we want to have as the term in the sum that we write down. So application of f to this index, and we go through all indices from the index specified here till the index specified here, and this is for what we go, meaning that to that the potential function is applied, right? And we get that, and what else could we have? Well, let's do something more interesting. Let's say we have 10, 20, and we have, I don't know, x plus y. We're gonna also write that formally. Maybe we don't know at all what x plus y is. Maybe we just want to specify a polynomial like that. No problem, this notation works. And if it is really meaningful what we are writing, well, we just have to look at the context and perhaps it is meaningful. So the notation is just notation for this structure, right? Okay, then there are some definitions, and they are really just definitions. We define that, and if, also define if I, not I, k. If k is just bigger than n, then all these, and it doesn't matter what are the things we sum over. Okay, I'll do now a silly thing, right? We just don't have anything to go over. There can't be this set. In this case, it's just empty because this set is meant as that, right? But now this is larger than this, and then nothing is in there, right? Of course, you could say, well, k is perhaps in there, but no, it just means that k is, if we write down this set, then k has to be at least, or n has to be at least equal to k because we really want to go through it. So in this case, this is just empty set. And I'll do a silly thing now, but what I mean, this is just defined to be 0. And here you don't have to have infinity. Infinity is just because you can then memorize it pretty good, that even if it is infinity or some silly thing, I don't know, then it is nonetheless defined as 0. Right. Okay. And this means repeat same as here, so then always, typical mathematical notation. And you have that such a product, and I talking about a product by writing sum of anything, no matter what it is, defined to be 1. And of course, this no matter what it is, we could just replace it by f of I, and because we have defined that this is actually connected to such a function. Right. All right. This is just how it works. This is just definitions, but those definitions are really meaningful. It has to do with some algebraic stuff because those elements are, well, those elements play a special role in algebraic structures, and so it turns out that it is meaningful to just define those things like that. But for real numbers, well, it's just that the element 0 itself has a special role in in real numbers, and the element 1 has special role in real numbers, and the role is just that 0 plus any element of real numbers is element itself. This property is called property of a neutral element, and same here with multiplication by 1 of any real number, we just get the real number back. And this addition or multiplication over empty set has to give the respective neutral element, that is element that doesn't change the number by applying to its operation that it is most reasonable to think of with. So 0 for plus, 1 for multiplied. Right. Now we have properties of sigma notation, and I won't prove that because it's excruciatingly boring. Properties of sigma notation. You also, well, if you want to prove them rigorously, at this point, even I say, well, okay, here, you really don't need to prove a proof to see that, but if you want to prove them vigorously, then you can do that, and I'll explain in a minute how it goes. But you can just write it down exactly like this, like with those dots of emission, and you can just see that it works. All right, properties of sigma notation. Well, one, and of course that is for numbers, right? But you can think that when we have an algebraic structure whose elements satisfy certain algebraic relationships, and you can think what properties carry over, and it's really, really simple. Okay, it's an abstract framework, you have to get used to it, but as soon as you get used to it, it's really, really simple. Okay, well, AI, and I just take some general numbers, AI, and as you see, I'm not using this notation with a function, it's not yet, is equal to, and we don't have yet notions that I'd like to use to actually say what we mean, and I don't want to confuse you with those notions, so let's write it just like, I don't know, a k pi, where, because by itself does not necessarily mean anything, but where bk bn is just elements of okay, I shouldn't write it as elements because let's write it as an ordered thing because there is some ordering, right? Because it could repeat, so I'm not allowed to write it as elements because elements could not repeat. Because so I take just an ordered tuple, just elements of with the order changed in any way. And there is, of course, a way to formalize that, but I don't want to confuse you more, so for now it's not that rigorously. With the order changed in any way. That is, I could now say, well, I just rearrange those, I don't know, like ak plus 1, an, and I rearrange that goes to this place, that goes to this place, and then after rearranging, I like give those rearranged elements names bk plus 1, so on till bn. And when I sum over it, then it is the same because the elements in total are just the same. And of course, you can see that it works because, well, we have commutativity. So we're just rearranging how I sum those things, right? And of course, that is commutative because addition in R is commutative, right? So doesn't matter. As you can see, you would not necessarily need to prove for that. Yeah. All right. What is next? Next is that if we have something like that and something like that and something like, and this is again meant as generalization, and I'll explain in a second what it is, even though it should be already clear, but I'll explain in a second because, well, it takes some getting used to. Okay, what do we have here? Well, we call our functions, right? And we have now, and this is just a general object, right? What I mean, of course, is, well, I specified it here on the top, but let's just specify it another time. That is just elements of R. Okay, now here, what is actually that? Oh, that is just elements of R, of course. And you'll see in a second why I'm going through exactly those. AK S. Here AK plus 1 S, right? AK plus 2 S, and so on until AK AN S, and we could continue and we go via AKS plus 1, AKS plus 2, could continue until a n wait, it's wrong because I want to keep that fixed now. Right, AK plus 1, s plus 1, and we are keeping the second one fixed, and so on, right? And then finally we get a okay. Well, I just lost by g is m. Okay. Okay, and plus 1, and we have now oh no. Okay, and it's not in global context. AKM A and M. Right. And what do we actually mean by that? Well, here we encounter this. Right? And this specifies such a function. It goes from K and to reals. But now we look at this function and we see what this function does while looking what is the running index, that is, what index of here actually comes into the sum. And here the index is of course I. We see this index I, that is the running index, that is the index that runs. And for each such I, we have to go through this now. For this object, oh, let's just write this object down and then think about what it is. But first, just really automatically, we just look at what it means structurally. First, on the level of a black box. This function does this, and then we look whether it is something that makes sense. But first, we just eliminate one level of black boxness. That is, we go on a simpler structure level, in that we write out explicitly a structure on a higher structure level, right? First, we just do that to understand what is going on. All right. Of course, again, no one does that, but let's do that. Okay, then we have that thing here. And we know what that is, right? We have an I, and we have for each I such an object. But we know what such an object is, right? Such an object just goes from SM to what? Well, and this thing is much more familiar when we fix an I. A, I, J. And here you have to keep track of what is fixed where. That is, for each such I, we actually have such sum over the evaluations of G. Well, of course, I'm not thinking clearly now. I'm too fast. Okay, we have such G, right? I'm just looking at this single object for a fixed I, because we are going through those objects that are now black boxed. We just think of them as black boxes with some content. But what we see, the connection of this black box to the higher structure level, is that we go through that varying I that indices our black boxes, right? So then there's a G for this object, and this G does what? Well, this G just maps a J, right? A running index. It just maps to a IJ. And this is now for fixed I, we said, because we were on the higher structure level here. And now we go on the lower structure level and remember what is kept fixed, right? All right. And then we see on this lower structure level that for fixed I, this thing would be I fixed, right? You have to go through many I's, but now we fix one I, and then we only have to go through G, right? All right. All right, this is just this sum, right? And for each I, we have that, right? So if I is equal to K, and here is K, and here is everywhere K. Keep in mind what is fixed, what is not, and where something is fixed, where something is not, right? Okay, then we go K plus 1, right? For K plus 1, we have here K plus 1 fixed, K plus 1 here, K plus 1 S, K plus 1 S plus 1, K plus 1. Okay, then we have we have to go through K, have such a sum for K, we have to go through K plus 1, have such a sum for K plus 1, and we have to go through everything until N, and we have to add up all those results. Okay. Well, that is, if we go back and insert that, right? We just remember what we had in the beginning. And in the beginning, we had I equal K to N, and we had J equal S M Aij is equal, and now we know here we go through all i's from K to N, right? This is what this function specified if you want to think again about how it comes about, right? And now we know what this object actually is, right? This object turned out to be that thing, right? But now, well, this is just a sum. Where this I is fixed, now we are trained a little bit to think in black box fashion. That is now for each I a black box, and then we look into the black box. And when we look into the black box, this I becomes the current value of I in this running. For example, K and so on. And so what we actually get is the following thing. AKS plus AKS plus 1 plus AKM. Then next value of I, we have to go through all of them. X, AK plus 1S plus AK plus 1, S plus 1 plus AK plus 1M plus, we have to go through all i's, right? And the final one is by N. And always keep in mind and make yourself keep that in mind. What we have, what we go through, what is fixed currently, and so on. Right? A and S, A and S plus 1 until A and M. This is just a notation for this. But no mathematician would ever write it down like this unless one has to verify some structural identities. Not ever to understand something like this. It is just intuitively internalized. This is like obvious, right? It is not obvious, but it's just you get used to it and you have it in your blood afterwards. You just work with it without ever writing down those functions. And actually, even in the at the stage of explaining, no one actually does that. Or maybe one time, but no one would ever write down those double sums in that fashion. No one would do that. Well, perhaps students in a homework, but other than that, no professors would ever do that. It's not done, really. So what I'm doing here is really like to say it in the language of mathematicians, since no one does that. It's like I'm explaining to you the multiplication table using addition of 1 plus 1 plus 1 plus 1 plus 1. That's basically what I'm doing. Because here's no multiplication, but you understand the analogy. All right. But it's normal because you see, it's not meant somehow to insult you. The thing is, mathematics students have to just realize those things, right? They have to realize it. And there's no shame in just getting an explanation for that, getting a proper structure explanation that explains every step, because that way you just be faster to realize that. That's all. There's no loss in it. Oh, okay. There might be loss in it if you come up with it yourself, and it might be that you develop better fluency in understanding that. And of course, if you just look at my explanations, but you don't make your own, you don't think about it on your own because you got an explanation, that would be, of course, wrong. Because then, yeah, then the explanation has hurt you and not brought you benefits. So what it should do. Right. So it might be that the usual way is better because here you'll be forced to understand yourself. But nonetheless, you still have this possibility because you could prove that, right? And I'll explain in a minute, as I told you, how to prove such things rigorously, but just write it down and do this manipulation with omission dots and see that it is equal. And of course, something like that is also possible with some indices and so on. So don't think that double sums are the only thing. It can go on forever. Well, not forever, but I mean for finite number of sums. Maybe even for infinite number of sums, but I think I haven't seen anyone who really writes that. All right. It's just you can inductively sum. And another note about this, it's not like you have to, when you look at it, you have to immediately see, oh, or see in your mind, oh, that is exactly that thing, and that every mathematician does, especially when they are like for some science. No one does look at that really like that. It's not needed because you just understand how it structurally behaves, and that suffices for manipulations. But it doesn't mean that it's not a good exercise for your mental imagination to just see explicitly in your mind what is kept fixed, what is summed with what, because if you manage to like learn to do that really explicitly, to do that in your mind, I can do that to some extent, then you'll be able to realize things without writing anything down. But okay, it's just side remarks. What do we have to do else? Uh, I didn't know actually most things, not just those. Okay. What else do we have to know about such sums? Okay, I'm not sure yet if I should mention anything else. Of course, you can interchange. Ah, okay. Well, something which we don't even think, but yeah, okay. If you have, but that is just done automatically. The order just doesn't matter. If you have I equal n and j equal nl, you have s equal p t, and you have this a I j s, then applying this double sum and think about what it is, like applying this double sum to this sum. You recall this is a black box, and this black box is somehow summed up in certain way. We have discussed that way here for elements. Here we just do the same with sums, so there is an additional step. So you will get like those black boxes summed up in that fashion instead of like here elements were summed up in that fashion, right? And this is of course same as here we have just one sum, and we have here inside the sum of element in this fashion, of elements in this fashion. Not just yeah, sum. I mean, finally, it is a sum of elements in this fashion because double sums evaluate to something like this. Okay, and of course, again, pay attention to what is fixed, what is not fixed. Well, that again, you could do a rigorous proof, and I'll tell you in a minute how, but you could also just write it down and see that it is true basically by I don't even think we need commutativity. We just can do it by associativity, but perhaps you also need commutativity here. So by commutativity and associativity, because like we go through indices in different groups, and so commutativity might be needed, right? And those are not necessarily empty questions what exactly we need, because in different algebraic structures you might have those properties given but those not given, and you might want to know what properties actually apply, what sigma properties actually apply. And yeah, I would say to be on the safe side, for everything we just postulate we need associative commutativity except for this one. And I think it's also the right thing to do. But of course, such a hassle is not necessarily, such a technical hassle is not necessarily favorite task of a mathematician to verify it. So we only need it when we only do that what operations are really needed, think about it when it is actually needed to think about it. All right, and of course that means that if we have some long chain of sums, and we just can do that in any way we like, right? We can put parentheses in any way we like, and then we sum over some. such number of indices, and here could be many sums. Okay, and that you could also prove, but well, usually it is not proved. It's just taken for granted. All right, because it's kind of obvious, right? So usually it's really not proved. We could think about a proof. I think I've thought about a proof once, but it's just too interesting. Well, you could do kind of, and it's not necessarily that trivial because you just have to see all combinations. You could do a kind of algorithmic parsing proof. You could think about how you can properly put combinations of certain algebraic signs like parentheses and elements and things like that. And you can think about how it interrelates with other putting those elements, but this is not necessarily trivial. It's not necessarily trivial, but it's usually just not done. And I think when I tried it one time, I only tried it in my mind without writing it really down. I didn't get to a conclusion because, well, but I was too lazy to really try it. So I only tried it in my mind to do a reader's proof for that. So, okay, if that holds, and we just say, well, we can uh, put parentheses in any fashion we like. And we call that parentheses means that applies as a whole, this applies as a whole, and usually it's of course done like with operations, but it's clear that here it is like as what sum we mean it and on what it acts, right? So yeah, if you're overwhelmed by this maybe unfamiliar degree of abstraction, don't worry. It's normal in the beginning. You just have to get some practice in dealing with such sums. And that's it. Okay, what else would you like to have? Associativity, commutativity, interchanging with sums. Okay. Also that we would like to have distributivity. Yeah, okay. And I have to think a little bit if it really works. AI, a, well, let's just such a sum. Okay. Let's say J and L and L B. Oh, what am I doing? Okay, we could, but let's not do that. Of course, we can just think of the sums of what they really are sums and can just give them different indices and things like that. So we are free to do things that make sense. Right. Okay, but I'm just writing down some customary relationships that can come in this fashion. Same as J. All right. And this is just a sum. This is just a sum. This is just a sum, so just a number, right? The distributivity law works, and of course we get first just that. But the thing is, we can, of course, do a little more stuff with that. Right? That is just that multiplied by that. Like this whole sum multiplied by this whole sum. Right, that is just distributivity law applied to those numbers. Remember, those are like black boxes, but they are actually numbers because we add and our addition is closed on real numbers. So that is a number, that is a number, that is a number. I can apply distributivity law, of course. I am. By the way, I have not yet established what real numbers are, but since this does not really this can be based off just your intuition. I will explain it in this video nonetheless because this notation is very useful. In particular, I use it extensively in the video and matrix and matrix. It would be a horror to do it without that. You can imagine you can write down things there without this and so I decided to explain that before introducing real numbers because you could just base it off your intuition how real numbers behave, you know from school how real numbers behave. But of course, actually, we have first to even make real numbers mathematically. We don't have real numbers yet. So this in the rigorous mathematical treatise, this comes, of course, after actually making the real numbers from basic mathematical assumptions and definitions. But we will do that, of course, in the calculus course. I just thought, well, I already give you that because, well, you know how real numbers behave. We have just established it rigorously, so you can now imagine we have established it rigorously, and then it works. Okay, here again, whole sum multiplied by the whole sum, but of course, you see here whole sum multiplied by the whole sum. But now recall what that is. Now recall in your mind that this is such a sum, and we can apply distributivity law for this number and this sum. So by the way, a very customary practice in lectures is just to leave out all the indices because it's clear what is summed with what. Oh, okay, I'm kidding. Usually it's not done like that, but sometimes it can be quite annoying when all the indices are left out. Yeah, but yeah, it's just what is done. I won't do that at least for now, but yeah, be prepared that it can happen. Of course, not in the context when the indices are clearly specified, but in context when it is actually clear from what to what we go in a sum. But yeah, sometimes it can be annoying nonetheless, especially when the professor thinks that, well, that's actually clear. Well, it is not clear because we had different sums in different contexts, or not necessarily sums, but other index objects and things like that. That can happen sometimes. So I'll try to pay attention to that in my notes. So we just apply distributivity law here, same way distributivity law. And here, now, for each I, we have that, right? Because this is just a number, independent of I, as you can see. It's no I. And here, in each term of this sum, we can now apply distributivity law for this number and this sum, which finally gives us the distributivity law for sigma, which amounts to okay, I already do that here same way, right? I is J, right? And this is the distributivity law. So by distributivity law, we can just put that there, and we can conflate those together. So we make a double sum out of this, and we conflate those together. But you saw it's just basic arithmetics, just written in a weird fashion of sigmas, of sigma notation. So, but there's really nothing about it. Okay, well, I think that's it. And if we will need our properties. Well, they are just derivable in same fashion. You saw this is nothing but just sums. Another remark about that, you see I'm using kind of always same stuff, A, I, J, S, like any kind of sum with specified objects in dependence on some indices could be written in that way, but of course it can, because A, I, J, S is actually A of I of J of S, where A of I of J of S just generalizes. If you don't understand that, it's no big problem. You will understand it eventually. Where AI JS is just a function for fixed JS. This is like the right way to do what we did here, right? The right way to think of it, I mean, the right way, the structurally smooth way, even though it might now look much more complicated, but this is actually not what is done. We just consider that as a function with fixed j and s, and this is a function, well, from some I don't know, we take, for example, that here, and we take mk, right? K to r. But this was for fixed JS, and now we have a fixed JS. So fixed JS gives us a function, right? So it's basically a function itself, which for each JS gives us a function AI of this JS, right? And that I'm writing it down here differently. Oh, okay, let's not write it differently to not confuse you. We just take G and S and we evaluate that. And this gives us a function AI. And you could forget for a second that, but just recall that it is fixed. And this function does something, right? And now, of course, for fixed. So, another time. We have J and S, just some fixed indices, and this fixed J and S gives us a function for each J and S fixed. We get a function actually, of course, should not write it like that. A of J S, and here I conflated, like A of JS gives us that function, and now AI of JS just gives us, that is, we evaluate this function of I, or well, it doesn't matter how we write it, but I'd like to write now comprehensively, right? All right, AIJS. So now S is fixed. Then J gives us a function, right? S is fixed. This gives us a function A J A of J of S. And for each J then, for each J, S is now fixed. Keep that in your mind, S is fixed. Then we go through all J's, right? We go through all J's, and for each J, for this fixed S, we get an object. what is this object A of JS? Well, we know what it is. A of JS just gives us a function that maps I to AI of J of S. Right. So it might be a little much, but you have just to think about it carefully. What I'm trying to say, okay, let's go do it very slowly. S is fixed. And for fixed S, if we are in this sum, right, for fixed S, let's say S is P, right? Keep that in your mind. We are going through P, right? Now forget the I sum for a second. Imagine there would be only JP. S was now P, and we have here JP. All right. Then for this fixed P, for fixed S, now chosen equal to P, we go through only J. That is, we go through all those indices from N to L for fixed P. A, N, P, A, N plus 1, P, A, N plus 2, P. All right. And we'd like to represent it now. What we said, S is fixed, and we'd like to go through all the indices through which J goes. And recall we had now just JS with fixed S. Okay. Now S is fixed, but actually there are different S, right? All right. But for fixed S, we have to go through all the things that correspond to J's, right? But that is for fixed S. For fixed S, we have to go through all the things that correspond to J's. And this indicates S fixed. And we have to go through all the things that correspond to J's. That's why this is a function. Example, S equal P. Then we just have the function that assigns to J always just some number that depends on J. We have to go through all J's there, right? Assign some numbers that depend on J. And here is P. All right. Now that is for one single S, but that is for each S. What does that mean? That means we have to go through all S from P to T. And for each such, we have such a function which assigns a J of P. So P S is now fixed value, and for each such fixed value, we have a function that assigns to J some number that depends on this fixed thing, because this function is for this fixed thing. For this thing that we have fixed for S, we have a whole function that assigns to the argument J a certain number. So we need information about the fixed thing, and we need information about the thing to which we currently assign. So about our function itself. So j goes to a of gt. And here j, for each j where the range of j was, right, p plus 1. Here we have a of j of p plus 1, and j is assigned with a of j of p plus 1. And that could be just any real number, right? So this construction is actually very general. Now recall that we imagine there's no I. Now I comes into play, but before that, recall that those functions, what we were actually interested in, well, for each such function, we wanted to take the sum, right? That is what those sigmas did. That is not j. We go for j. So let's denote this by this going for j. But j went from n to l. Right. J went from n to l. Okay, that is for p. We have to build this sum, but now we have to sum all those. Right. So here, final sum over g for the fixed value of s. Right. And here the fixed value of s is what? Well, the final value of s, namely t. Right. So what we have is t so, and this would be this double sum, right? And we see we can really construct it we see that this index notation that we had there, a js now, right? We omitted I, that this actually corresponds to such functions defined at indices. And so this notation with indices is really very general because we could take any such two-iterated function. Two-iterated function, I mean that it is function that assigns to indices functions. All right. And now we add our I. And that just means what? Well, now we have this I in game, right? S is fixed. And for each fixed S, right, we have same game. We have something that assigns to an index a function. But this is now for each S, right? So what we have in total, S assigns to that S assigns where A of I j of j of s is a map, and map and function I use interchangeably as announced, is a map that assigns to each j for fixed s, for this fixed single s, and for each of them, to each j, a map a then does the following. Or let's call this map. Okay, we should not. Yeah, well, let's do it because we assigned that for each j, right? But now for fixed s, right? So this is mapped to a of I of j of s. Again, keep in mind what is fixed. S was fixed. We go through all S, but now we are at a single S and it is fixed. And for each such S, what is happening? Okay, for each such S, we have an assignment rule. For what? We have an assignment rule that assigns to each J for this fixed S. Keep fixed S in mind. So now we also are at a certain J. And for this certain J, a map is assigned. A map that now goes through the last thing or the first thing, depending on how you see it, that assigns to i's certain numbers, depending on this fixed j and s. That is what we have in total. For js that really go through all j, all s, we have every time a map that does this thing. That just for each I assigns this thing. And this is really, we go through all of that, we fix each time that, we go through all of that, we fix each time that. And so we have actually j, or I mean the range of j. So that is the where the index range, the index j ranges from. And this is number of the indices in the range multiplied by the number of range of S maps, right? And each such map assigns to I something. So, and of course, to be just, we could just write that just as indices because that's easier than to write those brackets. But we could also always write those brackets. So you see those double, triple, or fourple, or I don't know what it's called in English, quadruple probably, quadruple sums are just functions that are iterated. There is an assignment of function to index, and there is an assignment to index of a function that assigns to indices functions. But as I told you, you don't need to understand it now, but it might be important that you see this flavor. Do you see this flavor? That you learn this thinking, what is fixed, what is not fixed, and this idea of fixing things and specifying things for fixed things, and that multiple things at once can be fixed, and that there could be that we build different levels of structure. All right, but this was an explanation why it suffices to actually consider this, that this is really general in truth. Right, so this is really functions on functions. Actually, no, it's just functions that assign to indices functions that might itself assign to indices functions. The functions assigned to the first mentioned indices. Right. Right. This is what is really going on. And this is why it works. It's really general formalism. Oh, okay. we are actually doing plus, so like 1 plus 1 is 2. But yeah, mathematicians can be sometimes, well, a little bit. They can overcomplicate things to have things much simpler in more general context. For example, to fully appreciate how powerful this notation is and how powerful dealing with it is, that it is not just for nothing. Just look my video on matrix operations and then you'll see, well, actually, if we wouldn't have this notation here, we would be really fucked. Okay, well, I mean, we would have to write a lot. Here we write little, but we write it on the cost of actually thinking in some complicated fashion. But again, uh, when someone looks at the sums, no one would really think, oh, that's actually that, and that works like that. No, that thinking is kind of internalized. And I didn't mean that necessarily in a way. So you have to learn now how it works, otherwise you can't proceed. No, I don't mean that in that way. I rather mean the opposite. No one really would think about that in that context. People just learn to deal with that and like discover those things intuitively. For example, I don't think anyone ever explained that to me. I just wrote it down now spontaneously because um, it's just you understand that it works like that with time. Yeah. So don't worry if you don't understand this explanation. Just go on, deal with your sums, and yeah, you'll see how it works after time. Okay. So then I should tell you how we actually prove those things rigorously. Rigorous proofs. It's called explanation note. Rigorous proofs for mathematical objects, for properties of mathematical objects, for properties of mathematical objects, that conceptually include iterations. That is, objects include iterations. That conceptually include iterations. Can often be tried to prove by induction. Can be tried to prove by induction. Okay, what is actually induction? That we'd like to discuss now. Now, recall your knowledge about the logical statements that you have acquired in the um, previous videos of this course. Right. Um, Induction. It's called induction axiom. we'll talk about that, I guess, in somewhat other fashion, where it might not need to necessarily be an axiom anymore. We'll prove it. Induction axiom. Oh, maybe not. I think we will, yeah, because it's kind of interesting what happens here. Oh, okay. Induction axiom. If there is natural number in n such that a statement P applicable to natural numbers and that includes a very broad range. Applicable for natural numbers would just mean that that is P of n is a meaningful mathematical statement. And you understand what it means. Ah, okay. P of m is a meaningful mathematical statement for each m element n. And what that means, you can define a function that assigns to each for each m element n for elements in n bigger or equal n. So if there is a natural number n element n such that first a statement P applicable to natural numbers, let's say larger or equal n is a well-defined function. So you can define such a function that to each m there is this statement P of m assigned, and an important thing about it is you could just think, well, P is just a function that assigns to any natural number some meaningful mathematical statement. But it's not what I mean, or defined function. What I mean is P has certain form, dot dot ha, and for any such natural number, you can insert, there is like a blank in P, so that in this blank there belongs a natural number. Why do I phrase it like that and do not just say statement about natural numbers? Well, that has a reason. For example, like examples. First, consider most natural examples. For each n element n bigger than 0, I don't know, 4n is divisible by 2. 4n is divisible by 2. Okay, obvious statement, right? But it is a mathematical statement. And let's say not for each, but say for n. For nn. For n in natural numbers, for n is divisible by 2. Then this statement is obviously applicable to all natural numbers in n bigger or equal 0, right? But this is a simple case. I would have just stated, well, a statement about a natural number, and then we could have just plugged in this number. But I want to cover also other cases, and those cases would be something like for an n previously defined and that is just we are, for example, in a proof and there's something previously defined like that. A of n mathematical object has a certain property. And why I have to phrase it like that, like very inconcretely, the reason is we have not yet encountered any mathematical objects by which I could phrase it in any meaningful fashion. A previously defined A of n mathematical object has a certain property. Again, this statement would be applicable to each n, but it is not a statement about natural numbers at all. That's why I phrase it that carefully. Might be confusing now, but in the end it will be really helpful. And if you would try to watch my course Basics of Linear Maps, you'll see that that is really used extensively. Right. Be applicable to natural numbers large or equal n. And we say a statement. So it is not just that, well, for each m, we just create a new statement or something. It is a statement that is really applicable to any natural number large or equal n. Okay, this is just the first condition. If there is a natural number n element n such that a statement p applicable to natural numbers large or equal n, and we have not stated yet what it has to do, is true for n, for this number n. This is the first condition. This given statement applicable to natural numbers has to be true for this n. Okay. Now second condition, and for each k that has to be true simultaneously. And for each k, v1 and v2. And for each k with k and bigger or equal n, we have that the implication P is valid for K. Let's write it really down like at least in parentheses, P of k implies P of k plus 1. That is, for each natural number, we have to have that when, for each natural number bigger or equal n, for this n, we have to have that if the statement P is true for this number, then the statement P is automatically true for the number k plus 1. And that we have to have for each number simultaneously that is bigger or equal to n. If we manage to find such a situation in which a statement P is applicable to natural numbers larger or equal some natural number n, right? So we found such an n, we found such a P, such that P is true for n, and simultaneously for each k in n bigger or equal n, we have that the implication P of k implies P of k plus 1 is true. Then, what is actually the axiom? What holds then? Then, the statement P is true for all natural numbers, of course, after n, because before n it need not even be applicable. The statement P is true for all numbers larger or equal n. In the beginning, you might think, well, kind of obvious, right? Because we just could stand at n, and at n, it is true, right? P true. Well, let's write it like that. P of n is true. And now we have explicitly stated when P of n is true, and for each k we have, for each k for n bigger or equal n, we have, so in particular for n, if P of k is true, then P of k plus 1 is also true. And if P of n is true, then you would say, and we have that, then of course, okay, it's no implication. It's now just going to n plus 1. And this, if we have that, then of course, if we really have both two conditions satisfied, P of n plus 1 is actually true. What's the problem, right? No problem here. And now, if we have that truth, of course, we can go further. N plus 2 and Pn plus 2 is actually true too. Because we stated that this is actually valid for each k n bigger or equal n, and we are iteratively establishing all the truths, right? So what's the problem here? I mean, why should we state this axiom if we can start an n and we can go always a step, and that way we would establish the truth for everything, right? And this is kind of obvious, right? Why do we state it as axiom and not just prove it immediately, right? We seem not even need any fancy tools to prove that. It's just obvious, right? Well, not quite. The problem is that you might think in some way of thinking that this is obvious, like I narrated it now. It seemed obvious in my narration, right? But rigorously, if you think about it rigorously, then the ability to apply it a finite number of times, that going from one to the other, establishing truth, going from one to the other, establishing truth, because the first one was true, and then automatically all the truths simply follow because we have the condition 2, right? And not, and here you should pay attention to the circumstance that we do not have at any point establish all the truths. We had the first truth, right? If the first condition is satisfied, and then we could establish the second truth using the second condition. But then only after we have established the second truth, we could establish the third truth. That is, for that, we always need to first establish the previous truth. But of course, in mathematics, everything is simultaneous. So you could think, well, we are going all these steps at once. Why not? Well, it is because structurally, what we are doing here is kind of depending on the progress that we have already done. And that this dependence, by going to infinity, leads to the application to the totality, is not necessarily obvious. So this could be an argument because why that is not obvious, even though, well, kind of seems like that. So we have to state it as an axiom. And why exactly? Well, you have to get to some level of mathematical maturity to appreciate what's actually going on. I would say there are people who would say otherwise. Like, it is understandable that what is going on is somehow weird, but in the framework that we have established, it should be not weird but obvious. But those infinite procedures, we just can't say about anything that it is valid in infinite context if it is just valid in finite context. We have to define that or to state that as an axiom. So there is no valid mathematical step that establishes this going as far as we want in the finite setting, implicating that we really can have everything in the infinite setting. So there we have not established such a mathematical step, and this is establishing of such a mathematical step. That is why we state it as an axiom, because we need that step. We need to state it rigorously. Right, but now, if on the contrary, it is all a weird, funny, abstract stuff to you, then let us look at some examples. And you probably know the story about the young Gauss, German mathematician of great mind, and who has, you know, who probably has the right to be called one of the greatest mathematicians of all times, like Euler. Now, I have to be careful to not name someone who would not necessarily be considered that, like Gödel, Hilbert, and people like that. Yeah. Jan Gauss has found a certain formula to do things like that in a matter of seconds. And maybe you know the formula. theorem. The Gauss summation formula. I think he was back then age 10 or 12 when he found that. The Gauss summation formula. For an element n have, oh, and now we can write it in a fancy notation. I think in terms of Gauss, this notation was actually not yet known, but yeah, I'm afraid to say something wrong. Well, of course, we need not start summation by 0 because that would not add anything, but we could also start by 0 for the same reason, right? That this can be actually computed very nicely as this thing. And you could check it on your calculator that it is valid for some examples. For example, for this example, it is indeed valid. Oh, well, let us check that. Okay. Well, let us check it like induction proofs actually done. Let us not waste time for just mindless checking. We have to prove that. And we now have this axiom of induction. If you wanted to prove that for each n element n this formula is valid, how would you go about that? You have to prove it for each n element n. So you have to do actually infinite amount of single proofs, right? Problematic, right? Somehow, yeah, not necessarily that cool. It would be never done. You could never prove that. But with induction, that reduces to two simple tasks. First establish validity for one. Even for 0. But let's start with 1 because for 0 the formula just is I 1 to 0 is of course equal 0 because because 1 is bigger than 0, right? First establish validity for 1. Of course, we could have then taken 0, but yeah. 0 we have established. I would like our start our induction for 1. 2. Then establish that indeed, the implication for our statement P that the formula holds for n. Then establish the implication. Well, what would be the implication in our case? Well, implication would be, of course, we go to the next number, right? We apply our statement that the formula holds to the next number, and we'd like to establish this implication. And what would be that? That would be just 2, right? Just apply the formula to n plus 1. Maybe it's a little bit too fast, so think about it, what it means to apply this formula to n plus 1. Then in the general statement of the formula, this formula is claimed for any natural number, in particular n plus 1. Right? For n bigger or equal 0, n bigger or equal 1, because for 0 we have already established, right? Then applying induction. Induction axiom. Right? Because we found a number for which this statement, this is a statement about a natural number, namely that the sum up to this natural number from the number 1 over the natural numbers that are in between is actually equal to this expression depending on n. Right? First, we establish the validity of the statement for 1, and then we establish the implication that this statement for n, because this is this statement for n, implies this statement for n plus 1. And by induction axiom, it is then true for all natural numbers. All right. And one is called establishing induction hypothesis. Oh, actually, no. Establishing induction anchor. Why would it be hypothesis if we establish it directly? Induction anchor. We anchor our induction. So we have to check our statement for 1. Now, in that sum, we have only a single sum term, right? We go from 1 to 1. That is single sum term, and that is, well, i's that participate is just I equal to 1. And this is hopefully hopefully equal to, oh, now you could write it down rigorously, but I just plug it in immediately. Our formula was n multiplied by n plus 1, but now n is equal 1 and divided by 2, which is indeed 1. Right, 2 divided by 2. I think that much I can calculate still, even though being a mathematician. Okay, and induction hypothesis. That implication step is called in establishing the induction hypothesis. Let n bigger or equal 1. Then have to prove, well, we have to prove the induction hypothesis. And that amounts to proving, and that is just any n, we have to prove it for any n, right? The induction hypothesis was formulated in that way in the axiom of induction, and to apply axiom of induction, we have to establish the prerequisites of the axiom of induction. Okay, we have to check this implication, and recall that for checking the implication was very conveniently defined, partly because of that. We have only to check the case when that is true, implies that indeed implies that that is also true. I have just to establish that this formula is indeed valid to check the validity of implication. Right. And this is basically the core meaning of implication, that it was defined in such a fashion like we have defined it. It is just because in some cases also other features of implication come into play. Right. So have to establish validity of that implication. Well, let's look at that and establish that. We want to prove something for this. So let's start here. And of course, Sorry. It's not called establishing induction hypothesis. I just recalled the terms. This thing is called induction hypothesis because we don't know yet that it is valid for any n. That we like assume that it is valid, but we assume that not in the sense of, well, we don't know that it is valid, but we are allowed to assume that it is valid. But we assume it only in the sense that for the implication, for proof of the implication, we assume that that is true because, as I said, that is the only thing we have to check to prove the implication, to assume that it's true and to show that the proof of this follows. Right, now we look at that. And we have to check that that is equal to that. Right? So where do we start? Of course, we'd like to use the induction hypothesis. How do we do that? Well, you see, recall what that was. And see that this is very similar to this, but like recall what this sum was. We just went here from 1 plus 2 plus 3, plus n plus 1. And we want now to establish here in it this sum because, well, we'd like to use that. And this is kind of similar as this. Well, seems a valid idea. How do we do that? Well, we just recall what that is and look at what happens. We take the last sum term away out of the sum and write the remaining terms again as the sum. Get exactly that, right? Just recall the definition of this. This was just a sum from 1 to n, so of course this is equal to this. Right? And I just tried to explain how one could come up with that. Just look for similar things and look what we'd like to achieve and try to combine it in sensible ways. In simple proofs, it actually always works. Now we use the induction hypothesis. That is this thing, right? We now have that because we want to have exactly this implication, so we assume the truth of that, right? And that use the induction hypothesis to rewrite this, because this is kind of similar as this, so it seems natural, right? But now we'd like to establish that this sum is actually this. But well, it doesn't look that bad, right? Well, what would anyone do at this point? Of course, bring to the common denominator, which is now 2, and we would look at that. Does it look really better? Because here we have sum, here we have product. Well, we have just to see that here we have a common factor. Common factor, we call distributivity law, which allows us to rewrite it like this. And see what this is. This is exactly that. That is, we have checked everything to apply induction axiom, and then usually people don't write like by induction axiom the proof is finished. We just finish in that point and make a nice square. The proof is finished. Usually people don't try this, as I say. So, okay, that was our first proof by induction. First proof in basics of university maths with using a sigma notation. Right, well. Okay, of course, such things are not, I mean, summation formulas, and there's not only one, there are multiples, right? Of course, such things are not necessarily not necessarily the only ones that can be proved by induction. There's a wealth of proofs that of actually not necessarily interesting statements. They are quite interesting things. For example, I don't know, things like um, what is that? Well, for that you actually do not need induction. But for example, for something like that, perhaps, and most surely for something like that. That one I do not even remember. That one, well, if we have that one, then yeah, that is the result. So let's don't list that. Okay, let's list that, but like because when you have the formula for that, we just write this as plus minus b, and that's it. And for that one, I don't even recall the formula. I would have to derive it myself. So this is another thing that can be proved by induction. And you could take a look at that homework. First, establish the formula and prove it by induction. Okay. Well, you are not yet that familiar with sigma notations, so maybe not. Okay, and another thing that I actually would like to take a look at, but I guess I don't even remember how it is stated, but this is another thing that is proved by induction, and this thing is actually useful. It's something like some estimate for how you can kind of this I don't know guarantee something like when you have something like that and you have something like that, you can somehow estimate, of course not quite like that, but for some certain x this is actually valid, or maybe the other way around. Well, minus one, okay, doesn't make much sense. Let's take one. Yeah, probably the other way around looks more solid that way. Wow, but actually, if we have 0, yeah, that works. Okay. 1, 2, n. Yeah, I think that. But that would be probably too trivial. Yes, that would be too trivial. So that can't be it. Yeah. So there is something like that. I didn't recall Bernoulli inequality, unfortunately. Though it's a useful tool in some proofs, especially in starting proofs in calculus. It's a useful tool. But yeah, so there are different things that can be proved by induction. And this is kind of the first time you actively get to interact yourself with mathematical technical formalism. Of course, by such proofs as that, that's more like technical writing down application of definitions and not much thinking, but there are interesting proofs by induction where you have to think a little bit how to do the proof of implication. The implication involved in the induction axiom. I don't have those in mind, unfortunately. Right. Okay. With that, I'd like to finish. You have encountered now the proof by induction, the induction principle, and you can now contemplate about that. You can just look maybe the net for tasks for proof by induction. I would say Bernoulli inequality is a very nice thing, but I'd like rather to prove it in the calculus course. And I would have to somehow come up with that because it's just I would not like to look it up. I would not like to look it up. I would like to like derive it like we are deriving it for the very first time. Right? Like to just understand what might be true and things like that. But yeah, I'll see how I go about that. But okay, let me finish with that. So sigma notation and induction. That's good. That's good.